We talked about carbonyl chemistry in the past with aromatic rings. We formed these ketones from the Friedel-Crafts reaction, of which I'm going to use a simple one here, just the acetyl ketone or methyl ketone. And we used hydrogen and palladium to get rid of that. That works because it's benzylic. Because it's benzylic, I can add hydrogens to that benzylic site without any problems at all. That does not work with acetone. If I take acetone, treat it with hydrogen and palladium, I get acetone back. Not a thing happens. What if I really wanted to get rid of that oxygen? Sometimes it's very useful to get rid of it. As we showed at the beginning of this section, carbonyls are a very powerful scaffold. I can build on one side, I can build on the other side. I'd like to be able to just get rid of it. I don't want a scaffold attached to my house after they fix the roof. I want to use it and get rid of it. Sometimes. Sometimes I'll leave it for the kids to play on. My dogs would love that. So we have to find another method to get that oxygen out of there. And it's going to tie into what we just did with imine formation. So what I'm going to do is I'm going to start you from the point of difference again. If I had acetone and I treat it with hydrazine, not something you ordinarily want to play with. It's used as rocket fuel, it's very toxic, things that are not friendly. So it's not something that we want to be involved with that we don't have to be. I'm going to use this, I'm going to use it with sodium hydroxide. So this is basic conditions. Now what I'll probably end up doing is letting the hydrazine react first to get the imine done and then making the solution more basic. So for the moment, let's leave off the hydroxide, and we'll actually just flow through to the imine formation as we did a moment ago. Okay, it reacts exactly the same way to form the imine. Now, overall, I want both those nitrogens out of my way. I want two hydrogens on that carbon, just like I got from hydrogen and palladium when I had an aromatic ring next door. I don't want to deal with this. I want this out of my face. So how am I going to do it? Well, it's a little tricky. Requires some work. Requires the hydroxide to help us. So this is the point where we need the hydroxide group. Hydroxide is a base. These are relatively acidic hydrogens. I form an anion. There's one we haven't heard many times in this course. Anion, negative charges on the carbon. That's weird. I don't do that too much. Kind of a strange one. With that, that anion is a real unhappy camper. Carbon as an anion is not a very stable place unless there's a reason to stabilize it. So it immediately will attack water. Now notice what happened on those steps. I moved the hydrogen from the outermost nitrogen down to the carbon via water, not via some mystical proton transfer. There's an intermediate agent going on here. So make sure you show that. And then we can do it again. And look what happens as we take off that hydrogen. Look at what we've just done. We formed a third bond between two nitrogens. What is that? Well, that would be nitrogen gas. One of the most inert and stable compounds you could hope for. As you breathe in, it's about, what, 75% of it. It does absolutely nothing. It comes out exactly the way it went in. And that's the case for most things. For nitrogen, in most cases. So as that happens, it separates entirely from the carbon. So I now have a second anion on carbon, but I have no nitrogen around anymore. It's bubbled out as a gas. It'd be a great way to see if the reaction worked. If you start seeing bubbles, you're in good shape. This will do a second attack on water. Do a second protonation of what was the carbonyl carbon, and now I've lost the double bond oxygen and replaced it with two hydrogens. This is called the Wolff-Kishner reduction. And it is a way of getting around the fact that normal carbonyl compounds, by normal I mean not lucky enough to be next door to a benzene ring, are not reactive towards hydrogen and palladium in the same way. You can't remove the carbonyl the same way. And because of that, you got to go about it a different way. Now, the next section, the acetals, is one of the more important ones in this chapter because it's one of the only ways we have of really protecting a carbonyl group, specifically protecting an aldehyde or a ketone. This does not work for acids, esters, acid anhydrides, acid chlorides. It is aldehyde, ketone, the end. And it's a very useful trick for us. It looks like this overall. We're going to take a carbonyl compound, an aldehyde or a ketone. We're going to treat it either with two equivalents of an alcohol or, more commonly, a diol, like ethylene glycol. And then what we're going to end up doing is getting rid of the pi bond, replacing it with two sigma bonds to oxygen. Now you'll notice what that does. We just took out the most reactive piece of the puzzle. It's a good trick. No pi bond, no nucleophilic attack. No pi bond, no protonation followed by nucleophilic attack. No pi bond, no problems. Not as much buildup of charge, etc., etc. So this solves a lot of our problems really fast. And it's reversible. That's the good part. So generally the conditions involved, and I'm going to show you the cyclic acetal because that's the one that's more common, are the alcohol or the diol involved and some strong acid. I'm going to favor sulfuric acid because that's a good one. And the leftovers, of course, 1,2-ethane diol, ethylene glycol. So in our first step, we're going to have nucleophilic attack by the oxygen on one of the protons of sulfuric acid, protonation. At that point, the carbonyl is ripe for nucleophilic attack. The only decent nucleophile in the neighborhood is the diol. So one of those alcohols has to step up to the plate, do the nucleophilic attack, break the pi bond, form the tetrahedral intermediate, and yada, yada, yada. Aren't we tired of hearing that yet? We now have an OH group and a tethered diol with a protonated alcohol attached to it. Now here's where things get a little different. We still have to get rid of that, so that's going to involve either another carbonyl or sulfuric acid's counterion taking that hydrogen off there. Neither of those is really great. That's one of the reasons your book favors that proton transfer jazz. Here's what's more likely. I have another molecule of this, so I'm going to write it as just R double prime OH coming in and taking care of that. So I end up with this. A neutral diol with an ether linkage. One alcohol derived from the carbonyl compound, one alcohol derived from the diol, and the ether also derived from the original diol. Now this doesn't help us get rid of it. The OH has still got, the original carbonyl OH has got to go. So we're going to end up doing a second protonation with a second molecule of sulfuric acid. Now we have water as a leaving group ready to go. But this is a tertiary carbon, so I can't do a direct SN2 on it unless I use an internal nucleophile, meaning I can't use the tethered alcohol. I can, however, use the ether, lone pairs, to do the job, much as I did for the imine. Once that's out of my way, I now have a carbonyl, but it has carbon attached to it. Instead of being protonated, it is now alkylated. But it reacts in the exact same manner. It's now just like the first step where I protonated the oxygen. It has a pi bond, but it also has a full positive charge on the oxygen. That's not a good place to be. So, one of the lone pairs on the alcohol that remains takes the job of nucleophile, forms the acetal ring, and leaves us now with another tetrahedral intermediate. After which, any of the species involved, more likely water than anything else, can come in, neutralize that, and I have my acetal. Now, as before, it's very critical that we get the water out of this reaction because this is all reversible. All the way back to the very first step. These are equilibrium steps. So I have to get that water out. We use what's called a Dean-Stark trap to manage that. You boil this reaction mixture and it selectively gets water out of it. We'll show you that in lab one day because it's a very useful trick to use. The point being, no water, no reversal, I can get the acetal. Now the halfway point where I have one ether and one alcohol is called the hemiacetal. And that's a big one because that's the linkage that occurs between, well, that's the linkage that occurs when you form the cyclic form of the sugars. So cyclic glucose has a hemiacetal as part of its structure. And you can see that if you want to go forward to chapter 25, you'll see it in all of the monosaccharides. Once they show you the cyclic forms, for instance, you can see it on page 968, but it'll be strewn throughout the chapter as they show you cyclic sugars. You'll see an ether right next to a carbon with an alcohol in it. That's a hemiacetal. When you see two sugars hooked together, like sucrose, for instance, that linkage is an acetal. You'll see it. There'll be, on one of the sugars, there'll be an oxygen that's between two carbons, and then off of that carbon will be another oxygen that has another carbon attached to it. So this has enormous biological relevance. This is the most important piece, arguably, of organic chemistry that carries forward to biochemistry, is acetals and hemiacetals. So you will see this many, many times in many different courses. It all comes down to the same basic trick from carbonyl chemistry. Use the pi bond. And then, if you need to, use the oxygen to get rid of it as water. That's what we've done here. So the cyclic acetal is useful as a protecting group. How do you think we might reverse this if we wanted to take that protecting group back off? Well, if we have to take water out to get it to go, what do you think is going to happen if we put more water in? Like if I take the acetal, the final compound here, and I put water in it and some acid, what do you think might happen? And the answer is it reverses. I get my carbonyl compound back. That has a great deal of use for me because I can now get on with business. I can control the reactivity. Now on page 705, your book gives you a good example of how this works, why it's useful. Some reagents will be selective. Sodium borohydride, for instance, is selective. It reacts with ketones, not with esters. Lithium aluminum hydride reacts with both. What happens if you wanted to react with the ester only? Can you do that directly? The answer is no. And that's where your protecting groups come into place. Get the ketone out of the way by a reaction that the ester can't do, like acetal formation, and then you don't have that problem anymore. So they show you a good example. I recommend you look at it, page 705. Okay. Now the next reaction that we're going to look at is a very critical one because, as I spoke about earlier, alkenes present a unique problem for us. Putting them in place specifically is rarely as easy as we'd like for it to be. I would love to see an alkene go where I want it, when I want it, and not have any troubles with it, but that just ain't the way it works. So I have to think there's got to be an easier way to do this. And there is. It also involves using that carbonyl to selectively attack the carbon. So what we're going to do in this case is we're going to take an aldehyde or ketone carbonyl and we're going to convert that carbon pi bond to oxygen into a carbon to carbon pi bond. We're going to get the oxygen out of there entirely. Now that sounds like it would be a little strange, and it is. There's a couple of ways of doing this. One, we could do an elimination. Generally, that doesn't give us good control of the regiochemistry of the alkene. At the bottom of page 707, your book talks about that. But what we want is very specifically to put a carbon in place where that oxygen is. Well, there's a way to do it, and it's called the Wittig reaction, W-I-T-T-I-G. And it actually takes advantage of the fact that we can do the same trick we've done already, using that selective nucleophilic attack on the carbonyl carbon. We have to create a reagent to do it with called a phosphorus ylide. This is a group where we have a phosphorus, generally with like 3 aromatic rings on it, and attached to that is a carbon, or more than one carbon, with 1 hydrogen on it. Now, this allows us some flexibility. It actually exists as what is called an ylide, hence the name, where the phosphorus has a positive charge on it, the carbon has a negative one. Guess what's going to be my nucleophile here? If you guessed the carbon, you guessed right. It's going to directly attack the carbonyl. Now, it has a bond still to the phosphorus on top of being negatively charged. So that nucleophilic attack does not get rid of the phosphorus. So I have my carbon with whatever was attached to it still attached to the phosphorus. The phosphorus is still positive charged, and now it's in proximity to a negatively charged oxygen. So very quickly, we form a 4-membered ring. Now, what's wrong with that picture? Well, it has ring strain. We don't have a bond angle of 109.5. It has some degree of eclipsing strain. It has angle strain. And not only that, look at this phosphorus. It has 3 huge aromatic rings on it. You thought you had eclipsing problems with a hydrogen. What do you think you're going to have when you got 3 aromatic rings on there? That's going to make a hell of a mess of this thing. So very quickly this is going to open, but it's going to open in a different manner than what we saw how it formed. When it opens, it forms a very stable phosphorus oxide, which does a lovely crystallization out of the reaction, so it's really easy to get rid of. And it forms an alkene, a second bond between the carbonyl carbon and what was the ylide carbon. So this is a very useful one because there's no ambiguity whatsoever on where that alkene is going to end up. Not a single bit. It's going exactly where we want it. So this one gives us a little bit of flexibility. Now, a couple of pieces we need to look at here. One, how did we get to the ylide in the first place? If we're going to make something that's charged, we need to be able to discuss where it came from. Charged species with carbons on them don't just appear out of the ether. They have to be made. We take what is known as triphenylphosphine, which has a lone pair. We use that to do an SN2 on an alkyl halide. Usually an alkyl iodide is a good one. We then have this. We have the phosphorus as a positive charge. The carbon is still neutral, and we have the iodide that was displaced, the leaving group, there as a negative charge to balance out the ion. That doesn't help us. I don't have a nucleophile here. I do not have a carbon with a negative charge here. Yet. Here's how that works. I have to take this SN2 product and I have to treat it with a strong base, which will deprotonate it. Now I have a nucleophile. And also it gets rid of the iodide because I end up forming like sodium iodide or something like that. So that helps. Now I have an active nucleophile. This is my favorite test question right here, is to see somebody do a nucleophilic attack when they don't have a nucleophile. If you've got no lone pairs and no charge on the carbon, it ain't attacking nothing. It's not going to be a nucleophile at that point. Don't use it as one. Okay, So the limitations here, of course, are that we're dealing with SN2 reaction. I can't have a tertiary alkyl halide. That works for me because I need at least one hydrogen there to make the nucleophile anyway. So those two pieces are tied together. You couldn't attack with triphenylphosphine if it were tertiary, and even if you couldn't make a nucleophile out of the product. So you get hit double time if you try to do the wrong alkyl halide here. But this reaction, I've done many of these in my life, and they're actually very direct. They work really well. Triphenylphosphine, maybe you don't want to be handling that too closely. You know, it might make some interesting genetic problems for me later down the line, but as far as doing the reaction itself, it works like a charm. And highly recommended. Puts the alkene right where you want it. Carbonyls are relatively easy to place. And so the most common way you're going to put an alkene in place is not by those elimination reactions that we showed you a long time ago, but by something like this. Because you have control. And you don't have to use extremely harsh conditions. And, even better, these conditions don't really interfere with other functional groups. A Wittig will not react with, for instance, an ester. So you make the active anion, the active nucleophile, the ylid, in a different flask, so you have no worries about the base deprotonating something it shouldn't. And then you add the carbonyl to it. Lickety split, it's done. I mean, in a couple of hours' time, it works like a charm. So, okay. Now, from this point, your book goes through some biological reductions. You can have a look at those. They're useful for you if you go into the biological realm. We're not going to talk about those in detail because we're sticking with the synthesis approach for right now. 1914, starting on page 711, is the last section that we're going to deal with in here in any detail. And these are what are called conjugate additions, where we're not going straight after the carbonyl. We're going sort of for its next door neighbor. Now that sounds a little silly, but it is essentially what's going on. We're using the word conjugate. If you think back to what we've talked about that in the past, that rings towards conjugation, right? We talked about this briefly when we did dienes in chapter 14, and now we're going to come back to it where we have a system like this, where we have an alkene conjugated to a carbonyl compound, particularly an aldehyde or a ketone. We call this alpha-beta unsaturated because the alkene is between the alpha and beta positions away from the carbonyl. Now from there, we have a choice of things that we can do. And it's going to depend largely on the nucleophile we use. So let's take a look at one of these here. I like cyclohexenone as an example. It works really well. If I treat this with a Grignard reagent, let's say I treat this with methyl magnesium bromide, and then I treat it with acid to protonate the final product, I'm going to get cyclohexenol. I'm going to get direct nucleophilic attack on the carbonyl, just like I always do. That is what is called a hard nucleophile, or a strong nucleophile. If, on the other hand, I use a weaker nucleophile, like I take this copper reagent, let's say it's dimethyl copper lithium. This is made from methyl lithium and copper iodide, copper 1 iodide. It's a metal-metal complex. It's a little bit weird, and you'll notice that we're now dealing with a transition metal, which means we have d orbitals, which means we change a lot of the properties of things. Well, now it's not such a hard hitter. It's not going to go straight for that strong nucleophilic attack. It's actually better matched electronically to the alkene carbon. So we're going to end up, in this case, going after the alkene carbon instead of the carbonyl. We're going to go for the far end of it so that we end up forming something like this. As an intermediate, the anion now lies between, it's now alpha. This is called an enolate, and we'll talk a lot about these in chapters 22 and 23. And afterwards, we treat this with mild acid as well. It also protonates, and I'm left now with substitution beta to the original carbonyl. You'll notice an important point here. I still have a carbonyl, which means I can take this product and now do something else with it. That's the biggest point of conjugate addition reactions. It allows us to work with two different functional groups separately. If I wanted to, I could use that anion for a nucleophile, and I will to great effect very soon, but not right now. So I now have the ability to split out this reactivity in several different directions. I can go directly after that carbonyl, or I can go after something that it's attached to instead. Later on, we're going to talk about how we could take off the alpha protons on the other side. So you can start to see how we could build in a lot of different places from the same very small amount of functional groups. Using the alkene, I can build in two different places here. The beta position by conjugate addition, the alpha position after the conjugate addition. I still have a carbonyl. I still have alpha protons on the other side that I can build onto. So this is getting to be one hairy scaffold, isn't it? Where we can actually build off in multiple different directions. Not a bad trick. So with that, we're going to leave off the discussion for Chapter 19. I think that if you understand what I've gone through, we're not going to go through the spectroscopy stuff. That's not stuff I really want to worry about right now, but we'll talk a little bit more about synthesis questions as we go into Chapter 20 and 21. But if you can go through what I just did in all of its pieces and make sense of it, then you should be in relatively good shape. These are the pieces. Now you have to put them together. So we'll deal with that a little bit later. The end.